Hello everyone. In this video, we are going to learn about the hidden Markov models. Hidden Markov models, it's a powerful tool in ML that is especially used for problems involving sequential data. It's used in various fields including NLP, bioinformatics, finance, and speech recognition. It allows to model the systems that have hidden states which can only be indirectly observed through a set of visible states or observations. Some of the terms components related to HMM. States. It represents the finite set of hidden states in the model. For example, in a weather prediction system, the states could be sunny and rainy. Observations. The finite set of observations that are visible and dependent on the hidden states. For example, for weather prediction, the observations could be dry and wet. Transition probabilities. This is the matrix of probabilities of transitioning from one state to another. Emission probabilities. Matrix of probabilities of observing a particular observation from a state. Initial state probabilities. This is the vector of probabilities of the system starting in each state. For example, let us predict the weather conditions rainy or sunny based on the observed behaviors, whether it is dry or wet. Let the states be rainy and sunny and the observations be dry and wet. As represented in this figure, the two states sunny and rainy, the transition probability from sunny to sunny is 0.7. From sunny to rainy is 0.3. From rainy to sunny is 0.4. From rainy to rainy is 0.6. So this transition probabilities could be represented as a 2x2 matrix. Like this. So this is representing the today's status and this is representing the tomorrow's weather. So the transitioning probability from sunny to sunny is 0.7, from sunny to rainy is 0.3, from rainy to sunny is 0.4, from rainy to rainy is 0.6. In addition to the transition probabilities, we do have the emission probabilities. That is, here in this problem, these are all the observations, say dry and wet. So this emission probability is going to give the probability of the observations given a hidden state. That is, the probability of dry given a sunny state is 0.6. Probability of wet given a sunny state is 0.4. Probability of dry given a rainy state is 0.1. Probability of wet given a rainy state is 0.9. Now the problem is to predict the weather conditions rainy or sunny based on the observed behaviors dry, wet. So we are provided with the transition probabilities, emission probabilities and the initial probabilities are also given. Probability of the sunny is 0.8, probability of the rainy is 0.2. Now we need to find the weather, we need to predict it based on the observations dry, wet, dry. When we say the observations are dry, wet, dry, on 3 successive days, it can be any of these combinations. The possible combinations are these 3 combinations. So for 3 days, the observations are given. So 2 power 3 combinations are there. Starting from sunny, 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 it could be rainy, rainy, rainy. So in between, there are 8 combinations. The possible combinations are given. Now the task is to find the probability of each and every sequence and whichever sequence is having the maximum probability, that is the weather. Let us consider the joint probability. P of A comma B equal to P of A given B dot P of B. As specified for these 8 possible combinations, we are going to consider the very first sequence sunny, sunny, sunny. From the transition probabilities, emission probabilities and the initial probabilities given, We are going to calculate this probability of the given sequence dry, wet and dry, and the first sequence sunny, sunny, sunny. This is computed in this way. So probability of dry given sunny, that is the first probability, and the probability of wet given sunny, and this is the next probability. Then the probability of dry given sunny, this is the next probability. Now for the sequence, for the weather, it's sunny, sunny, sunny. So for day 1 it is sunny. So we are considering the probability of sunny. Then day 2, the transitioning is to sunny again. So S to S. So probability of sunny given sunny. And on day 3 again there is a transitioning from sunny to sunny. The probability of sunny given sunny. So upon applying the values for all the given probabilities, that is probability of dry given sunny is 0.6. Then probability of wet given sunny is 0.4. Probability of dry given sunny is 0.6. Then the initial state probability for the sunny state is given in the problem as 0.8. Let us include that value 0.8. Then the probability of sunny to sunny transition is from the transition probability matrix, it's 0.7. We are including it. And again, probability of sunny given sunny, the transition to sunny from sunny, that's again 0.7. When we are finding the product of all these values, this is the probability. So probability of dry, wet, dry for the sequence sunny, sunny, sunny is 0.056448. For this combination, we have computed the probability already, that's 0.056448. Likewise, we need to compute the probabilities for the other sequences. For the sunny, sunny, rainy sequence, the probability is 0.004032, and for the sequence sunny, rainy, sunny is 0.031104. For the sequence sunny, rainy, rainy is 0.007776. For rainy, sunny, sunny, the probability is 0.001344. And for the sequence rainy, sunny, rainy is 0.000096. And for the sequence rainy, rainy, sunny is 0.002592. For the sequence rainy, rainy, rainy is 0.000648. Out of the calculated probabilities for all the 8 sequences, we find this probability to have the maximum value. That is for the sequence sunny, sunny, sunny. For this sequence, the probability is 0.056448. So this is the sequence. The most likely sequence of states for the observations dry, wet, dry is sunny, sunny, sunny. The joint probability of getting a particular hidden sequence and the observation sequence will be, this is the formula based on which you have done all the computations. That is, the probability of the observations and the states, given states is, we need to find the product of the two probabilities. That is the probability of the observation given the state, and this is the probability of the state, and this is the previous state, the current state, and this is the previous state. This is the formula which gives the joint probability of getting a particular hidden sequence and the observation sequence. Thank you.